before we move on to defining the vector derivatives in the curvilinear coordinate systems, for example, the gradient, divergence, and curl, we'll look at how do we actually define unit vectors in these coordinate systems. So in the Cartesian coordinate system, we had these constant unit vectors, I, j, and k. However, in the cylindrical and spherical coordinate systems, the unit vectors at a point pointing in the r, phi, or theta directions might vary as a function of position. So in general, we can write a unit vector for the ith component. So I can say I hat sub I is equal to d by dxi, where the dxi is the coordinate that we're interested in. Along with that, we're always going to have the scale factor. So whenever you see a dxi, there's always going to be an hi with it. And we're taking the derivative of the actual vector at that point. Okay, so that's a definition, but in general, we can't always evaluate this directly. So oftentimes we write our vector in terms, we've specified our coordinate system in terms of how it relates to the Cartesian coordinate system. So in the Cartesian coordinate system, we have A is equal to, we have our x, y, and z, and those are multiplied by the corresponding unit vectors, which in the Cartesian coordinate system are constants. So for this one, we can just evaluate it directly. In each case, if we just take dA by dx, all we'll get is I, because dy by dx is 0 and dz by dx is 0. These are independent of x. If we take dA by dy, we'll just get j back, and if we take dA by dz, we'll get k back. However, in a more complex coordinate system, the relationship between x and the coordinates that we're using might be a combination, so we have to take partial derivatives. So we can write this out as 1 over hi, and then in parentheses I'll write partial derivative with respect to x times partial derivative with respect to xi. So I'm taking the partial derivative of a, the vector, with respect to x, this x, multiplied by partial derivative of x with respect to the coordinate that I'm interested in. Because these are partial derivatives, I have to add up all of the components. So I'm going to have also partial by partial y, and partial y by partial xi, and then I'm also going to have partial by partial z, partial by partial xi. Okay, so in each case, I'm taking the partial derivative of the vector a with respect to the Cartesian coordinate, and then multiplying it by the partial derivative of the Cartesian coordinate with respect to the coordinate that I'm interested in. So I'm expanding this out using the chain rule, right? So dA by dxi is dA by dx times dx by dxi plus dA by dy times dy by dxi, and so on. This simplifies a little bit because these terms we already know from our unit vectors in the Cartesian coordinate system. So this one corresponds to I, this is J, and this is K. So it's really only these derivatives that we have to evaluate each time. So I'll put a box around that. This applies to any coordinate system, assuming that we know the scale factors for that coordinate system. So, for example, I'll work out what the unit vector in the r direction is in the cylindrical coordinate system. So, I sub r is equal to d by d r. The scale factor for r is equal to 1. So I'm taking the derivative of a with respect to r. And that means I need to take, so I'm going to put 1 over 1 out front here. This is my hr. And then in brackets, I'm going to have dx by dr is cos phi. So I'm going to have cosine of phi times I, because I is dA by dx. And then I'm going to have a plus. Now, dy by dr is sine phi. So the y component here is going to be sine of phi times j. And now dz by dr is equal to 0, because z is just z, it's not a function of r. So I can close the bracket here. So in fact, the unit vector in the r direction is cos phi times I plus sine phi times j. And that points in this direction here. So that's my IR. If I do the same thing, we're using this template here, working out the unit vector in the phi direction. So now I have d by d phi, and the scale factor is r of a. You'll find that it works out to negative sine phi times I plus cos phi times j. And again, dz by d phi is 0. Finally, if I work that out for the z direction, this one is somewhat trivial because z is just z. This one just works out to k. So drawing these unit vectors on here now, the unit vector in the phi direction goes off this way, and the unit vector in the z direction is just equal to k. So I have this orthogonal coordinate system now, but it's a function of position. So if my A moves around, the directions of those unit vectors changes. So try it for yourself. Use this template and try to work out by hand how the unit vectors look like in this coordinate system. We can do the same thing in the spherical coordinate system. So if I say I sub r here, it's d by dr. Scale factor for r in this coordinate system is 1 of a. So now I'm going to have non-zero components for all parts of this vector. So I'm going to have, if I take dA by dr, for each of them I'm going to have sine theta cos phi times I plus sine theta sine phi times j and then in the z direction I'm going to have just cos theta times k. So that's in the r direction. So my unit vector in the r direction points here straight out parallel to the r vector, because in the spherical coordinate system the r vector points all the way out to the radius, whereas in the cylindrical coordinate system it's always parallel to the xy plane. So that's IR. I sub phi in the spherical coordinate system, we'll find actually works out to the same as what it was in the cylindrical coordinate system. Because the scale factor in this coordinate system is r sine theta, so the sine thetas are going to cancel out when we work out these derivatives. So I'm going to end up with negative sine phi, and I'm going to have positive cos phi. And the z component is 0. Okay, so the unit vector in the phi direction actually goes out parallel this way, and it always remains parallel to the xy plane. So that's I sub phi. The last one is I sub theta. Okay, so when I work that one out, the scale factor is r, and so what I'll end up with is cosine theta cosine phi in the x direction plus I'm going to have cosine theta sine phi in the y direction, and then plus minus sine theta in the z direction. Okay, so that is the unit vector in the theta direction, and that always is going to be tangential to the theta direction here. So this is my I theta. And again, we have an orthonormal basis for this coordinate system. So that's the definition of the unit vectors in the curvilinear coordinate systems. This is the template that you need to remember to work it out for any coordinate system. What you need to know is the scale factors for each of the coordinates in that system. In the last video of this sequence, we'll look at how to interpret the gradient, divergence, curl, and some of these other operators in the curvilinear coordinate systems.